Technology Week, now in its 5th year and being hosted virtually for the first time this year. Virtual gatherings are new terrain for all of us, and yet, in essence, we are still doing what we have done for the last several years when we met in the Los Altos Library's Orchard Room. And now, because of virtual meeting capabilities, we can expand beyond the fire marshal's 100-person room capacity. So, thank you for coming along with us as we use technology to bring us all together. Hi, I'm Cindy Hill, the president of the Los Altos Library Endowment, which is sponsoring tonight's speaker. I thank you for tuning in after a full day of other activities. I'd love to know where you all are located, so if you would like, please type in the chat box the city in which you live. For more than a decade, the endowment has given continued support to the library's science and technology collection. The endowment also sustains the complete collection of the great courses of audio and video CDs in the Virginia Whipple collection. That collection contains over 1,200 courses. This unique educational source is available either online or through the library directly. The endowment has also funded the classical music collection and an electric vehicle affectionately named GoGo Biblio, which is our own mobile library that travels through the local community. You may have even seen it downtown or on one of our local streets. We also support children's and other programs as requested by our community librarian. Some logistics as we get started. Dr. Diffenbaugh will answer questions at the end of his presentation, so please type them in the chat box and they will be read back to him. This presentation is being recorded and will be available soon on both the library's website and on the foundation's website, the endowment's website. Tonight, we are honored to have with us Dr. Noah Diffenbaugh. Dr. Diffenbaugh is the Cara J. Foundation Professor and Kimballman Family Senior Fellow at Stanford University. He studies the climate system, including impacts on agriculture, water resources, and human health. Professor Diffenbaugh has received the Holton Award from the American Geophysical Union and a Career Award from the National Science Foundation. Talking about a subject that deeply affects all of us, Dr. Diffenbaugh will enlighten us with his talk, Is This Global Warming? One fun fact about Dr. Diffenbaugh is that he grew up surrounded by redwoods in our own Santa Cruz Mountains, just above Watsonville. Now, I'm pleased to introduce Dr. Noah Diffenbaugh.
Hello, everyone. Do you all hear me okay?
Loud and clear.
Okay, perfect. All right. That is great. I'm really pleased to be here tonight, and I'm going to talk about this question that I get frequently: is this global warming? And this is a question we are all living with year in and year out here in California and around the world. So I don't need to tell this audience that we are experiencing a spate of extreme events around the world. Here in California, we've had a series of extreme events in the last several years: drought, flood, heat, and obviously fire. So this question of that I'm going to address tonight is essentially, was the extreme event, whichever one that just happened in wherever in the world, due to global warming? And this question has been getting, for scientists, we've been getting this question closer and closer to real time, and now we're even getting. I get this question before an event even happens, when the event is forecast to happen. And I started my PhD 20 years ago in September of 2000. And back then, if you saw or heard a scientist on the record answering a question like this, it would be some version of "we don't do that." And that's really changed over the last 2 decades. And now you might find even something like this answer, which is an actual quote, somewhere between 0 and 100%. And that's not wrong. That is not a wrong statement, but it's also not entirely useful, because 0 to 100% is a pretty big range. So what I'm going to talk about tonight is how we go about trying to answer this question in a way that's scientifically tractable and practically actionable. And the framework that we use is essentially a risk framework. And I'm going to talk tonight mostly about the hazard, mostly about the heat waves and precipitation and droughts and wildfires, the physical hazard that we experience. But it's really important to note right at the outset that the risk is a function of not just the hazard, but the relationship between the hazard and the exposure and vulnerability. So what is exposed? People, ecosystems, infrastructure, and the vulnerability of what is exposed. And all three of these dimensions come together to create risk. And by using this framing and asking questions about the probability of each of these components of the risk, we can pose hypotheses that are objective and testable, and hence scientifically tractable. And the results are actually practically actionable, because it's difficult to make a decision based on somewhere between 0 and 100%. So our goal is to have a framework that is practically actionable, because the answer to this question is important for a number of decisions that society is facing. So a key component that I want to emphasize to you is that when I make public statements, such as I'll make tonight, when my research group makes public statements, we base those statements on peer-reviewed research. And this is a key underpinning of answering the question of, was this event influenced by global warming? Is having an objective, hypothesis-driven, quantitative framework for answering that question. So why might we be concerned with whether or not global warming is affecting individual extreme events? It's because we are altering the Earth system. We're altering the chemistry of the atmosphere and ocean. On the top, you see the Keeling curve. So this is the concentration of carbon dioxide in the atmosphere over the last half century. And we have added about 100 parts per million of CO2 to the atmosphere over the last half century. Concentrations are now higher than they've been certainly in the last 3 million years from geologic proxies, and only rarely have they been higher in the last 20 million years. And that's altering the chemistry of the atmosphere and the ocean. The chemistry of the carbon in the atmosphere is changing, consistent with the burning of fossil fuels. And the chemistry of the ocean is changing. And we are observing the acidification of the ocean as a result of the emission of fossil fuels. And in addition to the chemistry of the atmosphere and ocean, the energy balance of the planet is changing. And this is a cartoon version of the greenhouse effect. So we have a pretty impressive atmosphere. It lets most of the solar radiation in it. Mostly the Earth's atmosphere is mostly transparent in the wavelengths that the sun emits. The sun is very hot and emits at very high energy, very short wavelengths. And most of that energy makes it to the surface of the Earth. And then the Earth is much cooler than the sun, and it radiates outward at a much cooler temperature, much longer wavelength radiation, and the constituents in our atmosphere absorb a larger fraction of that long wave radiation from the Earth than the short wave radiation from the sun. And this is the essence of Earth's greenhouse effect. Earth's greenhouse effect is very important for life on Earth. We can construct a simple energy balance model. I'll be doing it in my undergraduate intro class starting tomorrow, in fact, and in a couple of class periods, we'll construct a simple energy balance model that will show using fundamental physics that without an atmosphere, Earth would be a frozen ball of ice. Earth's temperature, Earth's radiative temperature is only 255 Kelvin. So Earth's atmosphere is very important for preserving liquid water on Earth, for maintaining liquid water for the life as we know it. And by changing the concentration of greenhouse gases in the atmosphere, we are changing the energy balance of the planet. And as a result of changing the energy balance of the planet, we are changing the climate system, starting with the global temperature. So this is data from NASA, and it is replicated independently by a number of groups around the world. So going back over the last 1.25 centuries, you can see each of these gray dots is a year. And it's expressed on this graph as a departure from the mean temperature from 1951 to 1980. So each of these years is the temperature value is expressed as an anomaly. You can see the 0 line. The 0 line is the 1951 to 1980 temperature. Temperature was anomalies were near 0 from 1951 to 1980. That's a good sign that the arithmetic is working. And what you see is, temperature varies from year to year. It varies from decade to decade, but it is through time. And when temperature is going up, scientists call that warming. When it's global temperature and it's going up, it's called global warming. So this is the basis of global warming. It's simply an observation. It's not a matter of politics. It's not a matter of belief. I'm frequently asked if I believe in global warming, and I frequently answer, if you believe in thermometers, you believe in global warming. It's just a measurement. And we can create a hypothesis right here in the Zoom of what might happen to extreme temperatures, for example, with global warming. If the whole mean of the globe was to warm by a degree Celsius, all else being equal, we would expect the distribution of daily temperatures to warm by a degree as well. And what that would mean is that there would be more hot weather, right? A larger fraction of the temperature distribution exceeding the old extreme, right? Greater fraction of distribution in what used to be the tail, and in addition, more record hot weather, right? If the mean warms by a degree, all else being equal, we would expect to have increased frequency of record hot conditions, or hot temperature conditions that are unprecedented in our historical experience. And in fact, we are seeing that. We're seeing that with record hot temperatures around the world, and I'll come back to those data shortly. But we are seeing increasing extreme events, and critically, we are experiencing increasing losses from extreme events. So what I'm showing here are data from the National Oceanic and Atmospheric Administration. And in each year, you're seeing both the number of extreme events that cause at least $1 billion in damages, as well as the total cost of those $1 billion disasters. So this is the impact of extreme events. One measure of the impact. These are inflation adjusted. I frequently get that question when I show this graph. So yes, these are inflation adjusted. But this is the cost, right? So this does not necessarily tell us whether the hazards that are causing these damages are increasing, right? Because again, as I mentioned earlier, exposure and vulnerability are both critical. So what about the hazards? And the reality is that we know from observing the climate, from networks of climate observations around the world, that the likelihood of many kinds of extremes has already increased. And this includes, in the US in particular, severe heat, heavy rainfall, and extreme storm surge flooding, such as when a tropical cyclone makes landfall, the extent of flooding from the storm surge from that landfalling storm. We also know from now hundreds of papers over the last 10 to 15 years that global warming has influenced individual events. And this is most of what I'll talk about tonight. And just to give you a preview, we have many papers on the recent California drought, and I'll show you some of the results from my research group. The flooding during Superstorm Sandy, we know, was made more, like that level of flooding in New York City was made more likely as a result of the sea level rise that's already happened. The 2003 European heat wave was the original event that was analyzed for extreme event attribution in the peer-reviewed literature. And other events in other areas, the recent droughts in East Africa, the recent drought in Syria that coincided with the California drought, and many other events. So how can I be so confident about that summary that I just gave? So what I want to do next is walk you through a little bit of part of the story of how we've, in my research group, gone about asking this question of, is this due to global warming? So many in the audience may have lived through the California drought. It lasted quite a while. In fact, we were able to publish a number of papers about it while it was still going. So this was a severe event. It was a record-setting event in terms of the physical hazard, in terms of the combination of low precipitation and high temperature, in terms of the snowpack minimum, in terms of the many other groundwater withdrawal, a number of other physical measures of drought. It was also a severe event in terms of impacts. More than 100 million trees died during that event, and we're still experiencing the impacts of that this year with the current fires. And it also had big humanitarian impacts, both on jobs, and also there were communities that were without running water for months and months and months on end. And I'll say as an aside that as a researcher who receives public funding, working here in California, working on the drought, our decision makers from the governor down to local municipalities were very open and eager to have access to the most accurate information, and critically to incorporate the most accurate information into decision making. So I'm going to show you a few results from one of the papers that we published on the drought to give you a sense of where we got some of the early work on this question in my research group of extreme event. So this is a very nice version of a figure that was in the paper, but a much nicer version that the Chronicle put together. And what you see here are three variables: precipitation on the left, temperature in the middle, and a soil moisture index on the right. These are from the US government. And what you see is no long-term trend in the mean annual precipitation in California. Very clear long-term warming in the middle, and an increasing frequency of drought periods, which you see on the right. So what the connection? If there's no change in the mean annual precipitation, how could there be a change in drought? And the answer is the relationship between temperature and precipitation, and in particular, the very strong effect that temperature has on moisture availability during periods of low precipitation. And so the first key finding of this paper, first big finding, was we didn't identify any drought periods in California's history that didn't have low precipitation. So key point, right? We did not find any drought periods that weren't associated with low precipitation. So low precipitation was a necessary condition for drought over California's history, but it was not sufficient, right? And so low precipitation years historically have been more than twice as likely to produce drought if they co-occur with warm conditions. And what has happened as a result of that long-term warming, if we just look at the recent period, is that because of the long-term warming, we're mostly getting warm years now. And in the recent decades, almost all the years have been warm, and the probability that that low precipitation years coincide with warm conditions, the probability that negative precipitation years produce drought, and the probability that any year is a drought, those have all doubled in the last 2 decades relative to the previous century. So even without a change in the long-term precipitation, we still have had a substantial increase in the frequency of drought periods because of the long-term warming, because of that critical role that warm conditions play through evaporation, transpiration from plants, evaporation from soil, melting of snow, the aridification from high temperature. So how do we test cause and effect? One limitation, the key point for how we answer the question of is this global warming, is that we can't put the climate system in a lab. So we can't run 100 or 1,000 or 100,000 controlled experiments. So we have to use climate models to do this, and this is essentially like when I was in 3rd grade science, and we tested the effect of different conditions on plant growth, and we had 10 milk cartons, and we cut them down. We put exactly the same soil out of the same bag in all 10 of the milk cartons, and we planted the same number of corn seeds in each of those milk cartons, and we gave exactly the same amount of water to each one, and we put half in the closet and half in the light in the window, and the ones in the window grew and the ones in the closet didn't. And the only thing different between them was the sunlight, right? So that's the kind of controlled experiment we'd like to run, but we can't with the globe, so we do it with climate models. And what we find is that just like the historical global warming occurs with human forcing of the climate system from fossil fuel combustion and land use change. Similarly, the response is similar for California. So we have very high statistical confidence that the human emission of greenhouse gases have caused the observed warming of California, and the observed low precipitation years that are also warm. And so this is essentially like flipping two coins, and we see this in the observations, we see this in the climate model experiments, that, you know, if you have two coins and they each come up tails half the time, you're going to get two tails about a quarter of the time. If one of those coins is still 50-50 heads and tails, and the other one's coming up tails 80% of the time, 90% of the time, you're going to get two tails a lot more often. That's what we see in the historical climate record of California and observations, and it's what we see as a result of anthropogenic global warming. So that's a brief example of analysis of the California drought, and we spent a few years. We had a few papers on the California drought. We had a few. We studied a few other events, heat and drought in the central U.S., flooding in northern India, right? And so different events in different places, and we started to wonder, you know, how generalizable is this, right? You know, rather than picking individual events that are interesting for whatever reason, can we basically do this everywhere, you know, in a systematic way, do this all around the world? And so that's what this first global paper was about. And so we basically did something like what I just showed you for the California drought, but we did it all around the world, right? Everywhere that there's reliable climate observations, we can do the observational analysis everywhere that there are climate models. We can evaluate. We have climate model simulations for the world, so everywhere we can evaluate at each location the climate model performance. And what we found is that global warming has already influenced record-setting heat events around the world. And if we look at the total global surface area where we have reliable observations, the global warming has already influenced, increased the probability of record hot events at more than 80% of the surface area. And what you see on this map here, the areas that are pink, that means that the probability of unprecedented hot event is 10 times as likely now as if global warming hadn't happened, right? And if we look, even in the areas that are the lighter orange colors, right, that's still doubling or tripling of the probability. We can do the same. We can do the same analysis for record wet and record dry events, and we find that for those, about half the surface area has already exhibited increased probability of unprecedented events as a result of the global warming that's already happened. Given what I told you about our work on the California drought and the role of the co-occurrence of low precipitation and high temperature in creating drought in California, you might be wondering, what about the co-occurrence of multiple conditions? So we've analyzed that as well. And we found, as you might expect, for those two coins, because the temperature coin is coming up warm so often, there has been an increase in the co-occurrence of low precipitation and high temperature globally, both in observations and in climate models with anthropogenic forcing, which you see on the bottom with the comparison of the historical and natural forcing. So what this means is that globally, we're much more likely to have these warm, dry conditions, and critically, different regions of the world are now much more likely to experience warm, dry conditions simultaneously. And that's important for breadbasket regions. That's important for wildfire risk. So what I want to talk about now in closing is our work that was just recently published in August, published in August, about wildfire risk in California. So, as you may have heard in recent weeks, the last couple months, The area burned is increasing substantially in California and more broadly in the Western US. So as you can see here in the bottom left, the area burned over the last 4 decades, the annual area burned has increased around 10-fold over the last 4 decades for the Western US as a whole. Careful analysis by colleagues John Soglu and Park Williams, published in 2016 and then confirmed in the US National Climate Assessment, shows that about half of the increase in area burned is attributable to climate change, and in particular to the effect of warming on the vegetation dryness, what scientists call the fuel aridity. So that is a substantial fraction, right? Half is a substantial fraction of the increase. It's also not all of the increase, and this is really important, right? So climate change has played a substantial role, and it is not the only influence. As I'm sure you are aware, here in California, we are in the midst of a historic wildfire episode. So we have the first 1 million-acre fire in modern history, modern California history, the first 1 million-acre fire here in California, burning now, just crossed 1 million acres this week. 5 of the 6 largest wildfires in California's recorded history have burned this year, just since mid-August. The Mendocino complex, was just in 2018. The Thomas Fire was just in 2017. The SQF complex, which you may or may not have heard about, has just crossed 160,000 acres in the last 24 hours or so, which will put it, it's likely to appear as the 20th largest in California's history shortly. So this has been a record-setting year in many, many ways. And of course, we've all been impacted with the, directly for those who have lost their lives, lost loved ones, lost their homes, those who have been displaced, and the millions of people who have been subjected to the smoke from these wildfires. So this has been an extreme event. So by coincidence, we had a paper published August 20th about analyzing the influence of climate change on the likelihood of extreme wildfire conditions across California, and in particular during the autumn season. The autumn season is when we have had some of the most devastating fires in California's history, some of the largest fires in California's history. And it's a time when the interaction between the seasonal winds, whether it's the Diablo winds or the Santa Ana winds, or in other parts of California in the West, the offshore winds have different names, but they're physically very similar processes that create these offshore winds, and we tend to get these in the fall here in California. And of course, here in California, our seasonal precipitation in terms of our mean climate begins in the autumn. And so the relationship between heat in the summer and into the fall, the onset of our substantial precipitation, and the episodes of strong winds, how these overlap, are critical for autumn wildfire risk. So that was the topic of this paper. And one of the findings of the paper is that the autumn seasons historically in California that have had a large number of extreme wildfire weather days, so days when the aggregate winds and humidity and antecedent temperature and precipitation that influence the fuel dryness, when that aggregate wildfire weather is at extreme levels, those autumn seasons have had much larger area burned than the autumn seasons that have had fewer extreme wildfire weather days. So again, not the weather component, right? The weather hazard is not the only influence on wildfire risk, but it is an important one. And when we look at the frequency historically of extreme wildfire weather days statewide in California, we find a substantial and statistically significant increase in the number of extreme wildfire weather days per autumn season. And you see that on the right over the last 4 decades, the frequency of extreme wildfire weather days during the autumn season in California has more than doubled. Right? So a substantial increase in the frequency of the conditions that we know elevate the likelihood of large wildfires. And so we can ask about the spatial pattern and how much the risk has changed in different parts of California already, as well as how it might change in the future. So if we compare the mid-20th century period with the current period, using a combination of historical observations and climate model experiments, like I've already mentioned, we can compare on the left the mid-century period with on the right here the current period that we're in the middle of now, and we see already, as was reflected in that statewide time series, we see already an increasing probability of extreme wildfire weather days in many of the fire-prone areas of California. And then if we look forward in the future, a world that where the global temperature falls in the range identified in the Paris Agreement, from the most ambitious goals of the Paris Agreement, 1.5 degrees of warming, to something similar, the level of global warming similar to that's implied by the commitments that the countries actually made in the Paris Agreement, which add up to around 2.7 degrees of warming. You can see that future over the next century is one of further intensification of wildfire risk in California. However, it's a world of less intensification than a world that exceeds the global warming targeted in the Paris Agreement. Right? So a world that continues along the trajectory we're on now, which of our current emissions trajectory, which is a world of 3 to 5 degrees of warming. That is a world with in which California can expect more than a doubling, in many cases, tripling of the frequency of occurrence of extreme wildfire weather days relative to the present. So there are 2 key messages here. One is that the more global warming we have, the more greater intensification of the kinds of conditions we've been experiencing with respect to wildfire weather. And less global warming will curb the increase in those risks, but we are already in a world of elevated of extreme wildfire weather conditions here in California. And even if the Paris Agreement goals are met, we can expect further intensification beyond what we've already experienced from 1 degree Celsius of global warming. So the good news is there is hope. This is a question that comes up a lot in my class, that students are often asking for hope. So with respect to the wildfire risks, we do have many opportunities to manage these risks. The vast majority of ignitions in California are human caused, both from human activities and from the electrical grid. We've had, obviously this year, the these huge fire complexes that we've had, were initially caused by the lightning strikes that occurred in the middle of August. But we've had, on the list of most largest and most devastating wildfires in California's history, we've had fires caused by lightning, as well as the electrical grid, and spark off of a hammer from a person working with a hand tool, sparks off of flat tires, and even this year, a pyrotechnic device at a party placed on the dry vegetation. So we have opportunities to reduce ignitions. The fuels also clearly matter substantially for wildfire risk, and in addition to the effect of global warming in fuel aridity and drying out the fuels, elevating the risk, the amount of fuel and the conditions of the fuel are also influenced by forestry practices, and there are many forestry practices that are well known to limit that risk, and including controlled burns. We also have opportunities at the individual level with home hardening and creation of defensible space. We have opportunities to manage our risk with how and where we build. And then our investments in fire protection resources are critical. The people and the equipment and the systems. And as CAL FIRE has made very clear in their public statements, the resources have just been insufficient to stop wildfires from becoming large, devastating events when there are so many fires burning simultaneously in a landscape that is so dry. And then lastly, as I showed you, in the long term, the level of global warming will be an important influence on the wildfire risks that we face in the future. More broadly, beyond wildfires, there are other reasons for hope. We do have the opportunity to curb these risks, and we know from the fundamental physics of planet Earth, the transition to a carbon-free energy system in the middle of this century, a net zero energy system, gives around a 50% probability of staying below 2 degrees C of global warming. And achieving that will require, that's a major transition. And there are lots and lots of areas where we need R&D, both how to design and engineer and build, and also how to manage and how to deploy and how to create policies and implement policies. So the window is open, but this would be a major transition. Meeting the Paris goals will require a major transition. And I'll close just by saying that as a member of the Stanford faculty, we had very exciting news in May, where our president of our university announced Stanford's commitment to building a school focused on climate and sustainability to help the world address these urgent challenges. So with that, I will say thank you, and I'm happy to take questions.
Well, thank you. So, Dr. Diffenbaugh, we've had 5 questions so far. So I'll start with the first one. China is the biggest carbon dioxide emitter in the world. Why has the Paris Accord been unable to force China to make substantial reductions?
So I think there's a few dimensions to that answer, to the answer to that question. And I'm going to switch PowerPoints actually to switch over to second PowerPoint that I have from class, because we're going to be talking about this in class. Is that the wrong? Sorry, this is reminiscent of teaching. Okay, so you're seeing a slide that has historical cumulative emissions by country, I hope.
Mm-hmm.
Okay, so I actually have from class right here, it turns out. This is the relationship between cumulative emissions globally and global temperature. And what you can see, I will not walk you through my handwriting here. This happens to be up from class. But we know that the more we emit total globally, the more global temperature will increase. So really the level of global warming is really a result of the total cumulative emissions. And if we look at the total emissions historically, which is what matters for global warming, you can see that there has been, we can track the time series of manufacturing and other economic activity around the globe through time over the industrial era. But what we see is the US is still the largest emitter historically for the total emissions cumulatively, which is what matters for the global temperature, and hence, as I've just showed you over the last 45 minutes, for the climate risks in different parts of the world. So we are, the U.S. is number one. Our fraction is lower now than it was in 1940, but we're still 25%, and we're still the highest total. China's has grown notably, as you can see in this figure. Secondly, if I can get this to advance, which I might not be able to. Secondly, our per capita emissions are number one for significant economies. So we are, and our per capita is more than twice China's, and almost twice Japan's, and more than twice the EU's, and more than 3 times the world average. Right? So cumulatively, we're still leading. Per capita, we're still leading. In addition, what matters is what ends up in the atmosphere, right? And so my iPhone that just rang with my timer, this was manufactured in China, but it's for my consumption. My consumption drove those emissions, right? And so this map here shows the embodied carbon in trade between different countries in the world, right? So a lot of a significant portion of China's emissions are actually for products that are goods and services that are consumed elsewhere. And then lastly, if we look at the time series of different countries, and this is a figure from The Economist maybe last year, what you see on the horizontal is the per capita GDP, and then on the vertical is the annual emissions per person. And what you see is actually for the development trajectory, China's actually on a much less carbon intensive trajectory than US, Britain, France, and Germany. India and Indonesia are on an even lower carbon intensive development trajectory. So all of this is to say that this is a global issue, and ultimately what matters for the climate system is the total cumulative emissions, and there isn't one country that can individually stop global warming from happening through its own emissions, and it is a massive collective action problem. And the U.S. bears more responsibility, and by responsibility, I just mean contribution to global warming. The U.S. has contributed more to the historical global warming than any other country, and has done so on a more carbon-intensive development pathway than the other large developing economies are currently on.
You have several more questions that have come in since you've been chatting. Here's one that I think is related to California, but I can also see it in Australia. What is the foreseeable trend for the next 10 years for fires? Will the forests burn themselves out in the short run and let less fires for a few years, or will the number of fires and acreage continue to increase?
Well, as Governor Newsom noted this week, that August complex that's burned 1 million acres, that one fire had burned more than all the fires, from 1932 to 1999. So, you can do the math with 4 million acres this year. That's by some estimates, 10% of the burnable acreage in the state. We're the highest year in recorded history previous to this year was 1.5 million. So I think as a citizen, I can say I hope we're not on a trajectory of burning 4 million a year. But if we do 4 million a year, we could burn through everything in a decade. That's just the arithmetic. That's not that's neither policy nor a scientific evaluation. So I think the more critical question, I think it's unlikely that all of the forests in California are going to burn in the next decade for reasons of both fire management and the odds of lightning strikes like we had this year. I think the more pressing question for the forest ecology is it's a lot warmer now than when many of these forests than their equilibrium climate, and for the trees that are burning, in many cases we now have evidence emerging that the succession, post-fire succession, is being affected by the new climate conditions. And so I think that's something I'm going to be interested in learning more about and watching as a scientist who doesn't study forest ecology, is what we see in the coming years with that, with the succession, the post-fire succession, because we know that so many of these California ecosystems do thrive on fire. They do, they have a fire ecology, but the fires that we've, the severity of the fires that we've had in recent years is really opening up the question of whether the succession will be the same in the warmer climate.
And so another question is, why are scientists having a hard time agreeing that global warming is occurring?
I know of no scientific disagreement about whether or not global warming is occurring. Again, if I'll just say it again, if you believe in thermometers, then you believe in global warming.
Yes, I did write down that sentence. That was a great one. And another one, what can we do as individuals to help reduce global warming?
So, I'll spare you I won't dig through my PowerPoints to my class. I got a slide deck on that too. So, our energy intensity in the U.S. is about twice, per capita energy intensity is about twice the lowest of the OECD. So Japan is pretty close to, its per capita energy intensity is pretty close to the bottom of the OECD. And ours is about twice as high as Japan's. So, you know, the real challenge, right, is, you know, we're supplying, you know, 500-600 exajoules of energy per year globally, and there's still billions of people in energy poverty. And there are fundamental human well-being that's enabled by access to modern energy resources. And so the real challenge with respect to climate change in the future is increasing global energy supply and access, and that's potentially, you know, fourfold, you know, for even not for a world of 9 billion Americans, but a world of 9 billion, you know, at the lowest per capita of the OECD. So substantially increasing energy supply and access, decarbonize the energy system for the reasons that we just went through and that are depicted here in my handwriting. As long as we're cumulative emissions, we're going to keep getting global warming. So stabilizing the climate system requires decarbonizing the energy system. And then 3, adapting to climate change, because we're not adapted to the climate change that's already happened. We're not adapted to the climate we have now. And even if the Paris goals are met, that's more global warming than we've already had. We'll get more climate change. So each of those is a major challenge, a grand challenge, and doing all 3 simultaneously is a grander challenge.
So I want to thank you for your presentation, and I want to let you know that there are several more questions and comments that we're not going to be able to get to. What I'm going to do is capture those and send them to you so you can see the level of intensity and interest that this group has had for your presentation. It's really been quite exciting to see all of the conversation that has been going on. So
fantastic. I look forward to experiencing the intensity of the conversation. And I'm sorry not to have experienced it in real time.
Yes, yes. So on behalf of the Lolly Board and all of our participants tonight, I appreciate the time that you've spent with us. And I feel like I am a student in one of your classes. And I would love to have grown those little seeds with you.
This is a board from my class, so you've gotten the real stuff, let me tell you. I've got another
I'm
one.
on a roll. I would also like to thank and acknowledge our behind the scenes. Oh, there's class number 2. I'd like to thank our behind the scenes folks, who include our community librarian, Bryant Bow, and the librarian, Devin Simpson. They've kept all of the things rolling smoothly as we've been able to listen to the professor talk. I also want to thank the Lolly Board for all their time and ideas for our first virtual event. And thank you to our virtual audience. It's been wonderful watching the chat box comments, and thank you for spending the evening with us. I look forward to seeing you all again at another Lolly-sponsored library event. And Dr. Diffenbaugh, when I ride my bicycle around the Stanford campus, I'm going to look out for you, because it'd be fun to meet you in person. Not run into you.
I am sheltering in place.
Okay.
Very safely.
All right, I'll see you months from now.
All right.
Again, this event has been recorded and will be posted to the library's website and also the Lolly's website soon. Good night, everyone, and sleep tight.
Thanks a lot. Take care, everyone.